A very good morning to all of you. Today we are going to study the last topic of our non-inertial frame. We have already covered a lot of material. The 4 lectures, lot of material is there. The first one was on linearly accelerated frame. Then we studied the rotational frame. Then there is a lecture on comparison between the rotating frame and the polar coordinates because it also rotates with the particle. Then there is a lecture on Coriolis and centrifugal force, the examples mostly, different examples grouped into different categories. And I hope you have seen all these lectures. And now the last topic of today is Earth as a non-inertial frame. So we will see the effects near the surface of the Earth, their movements, and how the Coriolis and the centrifugal force they affect those movements. Okay. So let us see what we are going to do today. So Earth as a rotating frame. First of all, we will see that centrifugal force, both centrifugal force and Coriolis force are there, which affects the movement. Centrifugal force is usually much smaller. So centrifugal force combines with the value of G, and that is G effective. That is the first topic we will study. Then we will study about the deflection of a falling body, the different approaches to solve that same problem. Then Foucault pendulum. Then the flow of wind over Earth's surface, some solved examples, and finally one assignment problem. Okay. So let us start Earth as a rotating frame of reference. So in general we take Earth as an inertial frame, but strictly speaking it is not, because it is also rotating. So it is a non-inertial frame, and we will see very interesting effects of the fictitious forces, which are Coriolis force and the centrifugal force both, on the mostly actually the Coriolis force, so on the surface of the Earth. And it looks quite real also. Now when you study the motion on the surface of the Earth, the motions mostly we see 2 different kinds of motion. One motion is vertical motion, and other is the horizontal motion. Now in the vertical motion, the case that we are going to study is that of a falling body. In the horizontal motion, we will study 2 cases, and one is Foucault pendulum. It is pronounced like Foucault, F-O-U-C-A-L-T. Earlier I used to pronounce Foucault, but one of our professor who was the first professor here in LNMIT in physics. He came from IIT Kanpur as a retired professor from there. He was Professor Katyal, and he told me, no, it is Foucault. So it is Foucault pendulum and movement of winds. So these are the 2 examples in the horizontal motion. Okay. Now let us see, this is the gist of the whole exercise or whole lecture. You have to be very careful with these steps. The first step to solve these problems is to choose a proper coordinate system. Now here mostly we have taken x, y, z, r, theta, z. These are the 2 coordinate systems we have taken. You can take anything. It is not that you have to take only x, y, z. You can take this also, that also, or any other coordinate system depending on the problem. What is the problem? So choosing a coordinate system, that is the first step that you have to do. And we will see as we go along that how important are they. Then resolve components of omega and v along different axes. So if you don't resolve it, if you don't take a proper coordinate system, often you will make mistake, and it's quite difficult. So it's better that first you choose a coordinate system and then omega and v, because mostly we will calculate the Coriolis force, because centrifugal force we have taken care of into the gravity. So you resolve them and then it is very easy. Coriolis acceleration minus 2 omega cross v depends upon velocity v. So that one must know that it depends upon the velocity v of the object or whatever. Centrifugal acceleration is also absorbed in the gravitational acceleration that we are going to study now, just now. So it is actually constant throughout, because it is just any object will experience that centrifugal force, even if it is at rest. So that is being absorbed into G effective, into the value of G. And we know that gravitation, this centrifugal force, is always away from the axis of rotation. So whatever the axis of rotation is, it is away from the axis of rotation. But we don't have to struggle much with this, because this particular centrifugal acceleration is being absorbed into G most of the time. Okay, so let us see. Centrifugal force with acceleration due to gravity gives effective G. So G becomes G effective. Let us see this picture diagram. Here, as you see, suppose say this is the Earth as a rotating system, and Earth is rotating with angular velocity omega. Now consider a particle over a point P over here of mass m. Now that particle will experience a weight, that is mg, and that is directed towards the center of the Earth. It will experience a centrifugal force m omega square r outward from the axis of rotation, not from the center, but from the axis of rotation. This is the axis of rotation. It is outward, m omega square r or m r omega square. That is your centrifugal force. Now what we do, that we want to make a joint force actually. That means we want to combine these two forces, that is your weight mg and your centrifugal force m omega square r. We want to combine these two forces into one force. So what is that? You can add the vectors in different way. Presently we have used the cosine rule. So you add these two vectors. You make a parallelogram and you add these two vectors. Now this lambda is the angle that this particle m is making with O. So this we call as latitude. Now the resultant vector is this diagonal, that is this yellow line I am showing, this is the resultant one. We call it MGE. Suppose say we combine both the together, because this is quite small. We combine them together and we call this as MGE. So this is our new gravity. Okay, new gravity. The gravitational force is now acting towards this. From O, it has been shifted to O prime. This distance is not this large, but it is small, but still, just for the diagram. So O prime is very close to each other. So obviously, this is O prime. That means it is shifted from the center. So now let us add them, mathematically. Like vectorially we are adding. So let us see what is the final formula. MGE, this is MGE, my final vector, is this square plus this square. So mg square plus mr omega square whole square plus 2 mg mr omega square cos 180 degree minus lambda. So this is lambda angle. This also is lambda. So this angle is 180 degree minus lambda. So this to the power of half. This square, there is a mistake over here. This half is not here. This half is over here. Okay. So this square plus 2ab, 2 a square plus b square plus 2ab cosine of this, and the root over of the whole thing. Alright. Now GE, dividing by n or cancelling n throughout, GE is g square plus r square omega to the power 4 minus cos minus t degree minus lambda is minus 2gr omega square cos lambda. Okay. Now omega is very small. This is very important that we are dealing with omega, so it is interesting to note what is the numerical value of omega. So omega is very small, that is 7.3 into 10 raised to minus 5 radian per second. So omega to the power 4 is neglected because that is much smaller. So this term is being neglected. So what we left is GE is equal to g square minus this term 2gr omega square cos lambda to the power of half. Yes, here it is written correctly. Okay. Now I take g square common, so obviously it is half, so it is g 1 minus 2r by g omega square cos lambda to the power of half. Make binomial expansion of the first order and keep the first order 1 plus nx, that is 1 minus half 2 cancels out, r by g omega square cos lambda. You multiply by g and then you get g minus g gets cancelled, r omega square cos lambda. So from the figure, this r, that is distance between the particle and the axis of rotation, this r is r cosine lambda. This is if you do it like this, so this is r cosine lambda, isn't it? R cosine lambda. If you draw a line over here, so it is r cosine lambda. This small r is r cosine lambda. So r small r is r cosine lambda. Substitute over here so that we know all the quantities. Now GE is equal to g minus r omega square cos square lambda. So this is my final expression, that the effective gravity, this I call as effective gravity, is g minus this term. If I put numerical values of this is 9.8 minus 3 into 10 raised to minus 4 cos square lambda. So you can see this term is really very small. So this term is very small. Effective value of g at any latitude lambda. Now what is cos square lambda? Now lambda is 0 at the equator. So cos 0 we know it is 1. So basically it is minimum there actually. And here at the pole it is cos 90. So cos 90 is 0. So there we get 9.8. So at the pole you get exactly the same. But at the equator you see the maximum effect of the centrifugal force. So this is an important expression, and now from the next time onwards what we will do, that we have to take care of centrifugal force anyway, because Coriolis force is depending on V. But anyway, if any body is having V, that body is there. So centrifugal force is always working, always acting on a body. So for that, finally the G, whenever the G is coming, in place of that G, we will put G effective. So we don't have to do the separate calculation for centrifugal force. So centrifugal force is now taken care of by the effect of effective gravity, that is GE. Fine. So now we are going to the next problem, and that is deflection of a falling body. It is a quite a interesting problem and little difficult problem as well. So now we will study the vertical motion. Motion along the surface of the earth. One type of motion is vertical, that is a body falling straight to the earth. Another is horizontal movement. There can be many movement of the winds, Foucault pendulum, a plane traveling, all those are horizontal movements. In between also we can study like projectile motion. If we know how to deal with the vertical and the horizontal, so we can take the components of the projectile in vertical motion and horizontal motion and we can solve it. Now, deflection of a falling body. Now, when a body falls from a great height, obviously it is having a velocity. So, because of the velocity, the Coriolis effect will be there. Centrifugal effect already we have taken care of in the value of g. So, we have to see that how Coriolis effect changes its motion. That is what our purpose is. Now it is being observed, and also through the calculations and mathematics we will see that a body which is falling straight under gravity, within gravity is the main force of gravity, that is the weight. When the body is falling vertically, there is a deflection of the body, and that deflection is towards the east direction. The deflection is towards the east. So because of Coriolis force, a horizontal displacement is observed towards east. Now, here we have to, understand the coordinate system, because this is very, very important. And unless you understand this coordinate system, it's very, very difficult, because this is a little bit difficult problem. So this is the diagram of the earth, a 3D diagram. Now from the center O, if I draw a line outward, this is actually outward, though it may not look like, it is outward. This is Z axis, alright. This axis, that is your earth, is rotating like this from the west to east. So omega is along this direction. This is the direction of omega. This is the direction of omega. Vertically upward from this point. This we have taken at lambda, latitude lambda. So this is vertically up omega. Now, how to find out the direction north, south, all those? If a man is standing over here and he wants to go to the north pole, he has to walk along the surface towards the north pole. So, if you put a axis parallel to the surface towards the north pole, that is the direction, that is your y-axis, and it is the direction north. Axis parallel to the surface of the earth towards the north pole is north. So this is your y-axis. The moment you define the y-axis and you call that as a north, other axes are defined. So x is the east, and that is, within the, if you go that side within, so that is your x. Okay, that is your east. As you can see over here, that other side is the east. Downward of y, this is north, that is south, that is east, this is west. So this is a complicated system. Now, in order to explain this, I have brought a ball, I think it's a basketball, yes. So through that ball, I will try to explain once again these axes, because it is very important that you understand the direction as well as the axis as well as the direction of omega very, very clearly. Okay, so let me show you the axis in this ball. Okay, this is a ball, a basketball, and so you see the diagram, you can see the diagram over there, alright, and let me show you over here, because this is a 3D ball. Okay, now your omega, first let us see omega. Omega is the most important one. Suppose I take a point over here So omega is vertically up because this is moving, earth is moving like this, okay, from west to east. So this is the omega. Omega is this. Now what is the z axis? Z axis is from the center. From the center, the axis that is coming out, the line that is coming out to the surface, that is your z axis. So this axis is omega, capital omega, and this is the z axis. Now what is the, you see the figure also, you see the figure. Now what is x? X is the east direction, so I can shift it like this. Just if I hold the pen parallel to the surface of the ball, then this is my east direction. And what is my y-axis? So this is x-axis. East direction is x-axis. And what is my y? Y, you hold this pen again parallel to the surface, so towards the pole. Because if somebody wants to move towards the pole, so this is the y-axis. So this is the y-axis, this is the x-axis, this is the vertical, that means the omega, vector omega, and this is the z. Z is the line that you draw from the center outward. That is what we see over there. So is this clear to you? Once again, maybe at a different angle. This is your omega, okay, vertical omega. This is your z axis. So we often resolve these actually along this and this, that is z and y. So this is your omega, this is your z, this is your x, which is your east. East is towards this direction, this is your east. And this is your y. Y is actually the north. So in terms of the direction, this is your north, this direction is north, opposite to is south, this is your east, and opposite to the west. This is your capital omega, and this is your z axis. So this is your z axis, this is your x axis, this is your y axis. Y axis is the red pen, y axis pointing towards north, and this is your omega. This is your omega, and this is your green pen is your z axis. I hope now it is clear to you. Fine. Okay. Now what I have done, this 3D diagram, whatever is over here, that I have changed to a 2D diagram. Now in the 2D diagram, again almost the same thing, lambda, z is away, omega is straight along this direction, vertically up, y-axis, it is starting a kind of tangent to the surface at this point P, so that is your y-axis. Where is x? X is going inside the page, inside the board. So that is your x-axis. So that is your east, inside the board. Now this is lambda, obviously this angle is 90 minus lambda, and this is again lambda. This should be very, very clear to you. This is your z-axis, this is your y-axis, x is inside the board, and omega is vertically up, and these are the angle, and it is rotating this way, so omega is up. So 3D diagram and the 2D diagram. Now when a body is falling from a height h, there is a deflection, a small deflection which is observed in the direction east. Okay. Now we need to visualize the problem. It is a little bit of difficult problem. that how the forces, velocity, Coriolis, all these things are working into the problem. So here, this is not from any book. This is just for your understanding purpose. Okay, I have made this table so that you can understand what actually is happening, the physics behind the whole problem. And then there are different solutions we will see. So visualize the problem. It is just for visualization. And we are not going to take anything from here. It is just for visualization so that you can understand the things well. First of all, what we do, we write omega in terms of k and j. That is your z-axis in terms of k cap and j cap. J cap is unit vector along y, k cap is unit vector along z. So omega cos 90 minus, that is sine, omega sine lambda k cap, omega sine lambda k cap plus omega cos lambda j cap. Now, it is not necessary that we always resolve. Depending on the problem, things are different. But here we need to resolve it. So that is many problems we do it. So this is a usual way and you should know how to do it. So I hope you should not have any confusion. The omega, the angular velocity of the earth, omega, which is a vector, it is written in the k cap and j cap, in terms of k cap and j cap, in that direction. Now, what you imagine that you see that there is a body at a height h, suppose say at a point P, this is at a point, some point P, okay, a mass, small mass m. Now that is falling vertically. Now this is dotted line is a vertical line, but it is not falling exactly vertically down, but there is little bit of shift towards the direction east. There is little bit of shift, small shift towards the direction east. Now in order to understand the physics of the problem, what I have done, that I have taken three different points. The first point is when t1 I have written, t1, that is t1 is 0. That is t is 0 actually. That is the first point. About to start. That means this particle is at rest. So that is your number one. V is equal to 0. Number 2, that is your t2 just after time delta t. That is the point 2. Here the point 2. Third is your t3, that is just after some more time, t3, that is t. That is the point number 3. So now let us try to see how the things are evolving and the physics behind it. So this is the omega I have written. Here I have made a table. Velocity, what is the velocity at these 3 points, and the Coriolis acceleration, that is minus 2 omega cross v at these 3 points. I hope till here it is clear to you. Okay. I have written omega. I want to see what is the velocity and the Coriolis acceleration at these 3 points. That is t1, t2 and t3. Correspondingly, these are 3 different points. Now, take the point number 1, that is t1 is equal to 0 or t is equal to 0. So here, the velocity is 0. So what is the Coriolis acceleration or Coriolis force, whatever? It is 0 because velocity is 0, so it is 0. Next point, as the body started falling, just it has started falling. That is t2 is equal to delta t, very small amount, after very small time. The body is falling vertically at that time. It is falling vertically, exact vertically. So my velocity is some magnitude I am not bothered about, but it is in a direction minus k cap because this is z direction positive. So I have written minus k cap. Okay. Now, what will be the Coriolis acceleration? Coriolis acceleration is omega cross v. So omega is this cross v. So k cap cross k cap is 0. Fine. J cap cross k cap j cap, j k, they are coming one after the other. So j cap cross k cap is I cap, but minus sign, so minus I cap, minus sign over here, so I cap. So Coriolis acceleration, whatever magnitude I am not bothered about, but it is in a direction I cap. That means eastward. Okay. So Coriolis acceleration, because of this Coriolis force, is eastward. Okay. So obviously the velocity, the acceleration is eastward. That means there is a velocity in the eastward direction, in the I cap direction. So now I go to the third step, because it is now falling. The body is falling. In the third step, what is happening is that obviously it will have the minus k, initial minus k. It is falling down. Whatever magnitude, doesn't matter. Minus k cap is the downward velocity because of the acceleration due to gravity, plus because of this eastward acceleration, a velocity in the eastward direction that we have added. So we have added is plus I cap, that is eastward. So minus k cap plus I cap, because of the Coriolis acceleration that we have seen in the step 2. Just after this, the velocity is in the I cap direction. So you have two components. Minus k cap is much larger, but there is I cap also a small component in the I cap. This is the third, at some just after that time t2. So now k cap and I cap both are there. Now let us see what is the Coriolis acceleration. So again omega cross v. So omega is k and k cap and j cap. So k cap is 0. K cap and I cap, that is k cross I. So k cross I is j. But again there is a minus sign over here. So it is minus j cap. Okay. From k. Now I will go with j. So j cap cross k cap. So I j k, j cross k is I. Okay. Then I minus I plus I. So plus I. Alright? Plus I. Then j cross I. J cross I. J cap cross I cap. So j cap cross I cap is minus k cap. Minus k cap and minus is plus k cap. Alright? Well, now as you see that this term, we have to understand what actually is happening. You see, initially, before that, we have only I. Okay. Now we are getting an acceleration. We are getting I is anyway there. That was the initial one. That has to be there. But now we are getting two extra terms. One extra acceleration. One in minus j cap direction. Minus j cap means southward. And one in k cap positive direction. This is k cap positive direction. Okay. But both are quite small, much smaller than this I cap. Because I cap is coming from much greater velocity, that is the vertical velocity which was initially there. From there I cap is coming. So that's why I cap I have written first order. These are second order, that is this minus j cap and plus k cap. So plus k cap, what it will do? It will decrease the velocity, vertical velocity, which was initially there. Initially it was minus k cap direction. The body was falling. Much higher velocity, much higher acceleration. But this is in the positive direction object. So it will decrease that vertical velocity, that is velocity in the z direction. It will decrease this downward velocity little bit. But this will give a component in the south direction, minus j cap. So you see, Now all these three components are there. But this component, I cap component, is the maximum component, that is the largest one. These are smaller. So these I have called as second order. This one is first order. So now the velocity that I am having after say point 4, if I draw, it will have all the components. That is your I cap, j cap, k cap. The falling body will have all the components. And interesting part is all these components will interact with this particular omega. And one component will interact, will give it to further another, that will again interact, give it to another, this will again interact. It will go on like this. The loop will go on. But the thing is, as it is going on and on, the things are smaller and smaller and smaller. Now, how to deal with this kind of problems? That is what we will see. I hope this table is clear to you, that how the things are changing as the body is falling down, how different components or velocity are created because of this Coriolis acceleration, because of this Coriolis force. Good. If this is clear to you, then we will go to the next step. That is the solution to the problem. There are different approaches to the solution. One approach is exact solution. Other one is approximate solution. Now, in exact solution also there are different methods of doing it. Briefly we will see what are the different methods. As I told you earlier also, that it is interesting to see that how a single problem can be solved in different methods by different ways. But we will not go into the details of it, because a lot of mathematics is there. So method 1 is very simple, very straightforward and rigorous also. So there is no approximation there, exact. You write omega as omega sin lambda k cap plus omega cos lambda j cap as usual. And V you write as Vxi Vyj plus Vzk. Okay. Then you write Coriolis acceleration minus 2 omega cross V. And just you do all the cross, and finally you group all the terms together with I cap, all the terms together with j cap, all the terms together with k cap. Now I can write that dvx by dt, because I have to find out in x direction, in y direction, in z direction. But z direction is okay, but mainly we have to see in x and y direction. What is the deflection? That is what we are interested in mostly. But we have to write all the three equations. That is dvx by dt, because every movement is linked with the other one. Okay. So dvx by dt is this, dvy by dt is this, and dvz by dt is this. So three equations we have to write, because this is an acceleration term, Coriolis acceleration. From Coriolis acceleration in the x direction, in the y direction, in the z direction, we have to write according to the unit vectors. So you are getting three different equations, but these three different differential equations, they are coupled with each other. And it is very simple, it's not very difficult. You can solve it, three equations and three unknowns. So you will get Vx, Vy and Vz. From there, you can find out the deflection. That is x and y you can find out, because that is what we are interested to find out. Because anyway, what is the x direction and what is the y direction? So x and y you can find out. Okay. Now, we are presently not doing it, because the solution that you will get in terms of t. And t we are not much interested, because we want to get it in terms of h. Now, we can convert t into h. The moment you want to convert t into h, then you need to do some kind of little bit of approximation. So presently this is the exact solution. We keep it in terms of t only. Okay. So this is one solution. Other solution is, this is again a different method. As I was telling you about order, it is with the order. Okay. So omega as usual we have written V01 v01, initially the first order actually we are taking. So you take minus gt, you know v is equal to gt when the body is falling under gravity. Now in place of g, we are writing ge, that is the effective gravity where centrifugal acceleration term is taken care of, minus gt into t, k cap, only vertical velocity. So here we are taking only vertical velocity. With that vertical velocity, you calculate or we calculate the Coriolis acceleration minus 2 omega cross v. So whatever we get I, we have seen there that the first one we get in the I direction. Now with that acceleration, you calculate the first velocity, first order, that is v1c I. From that first order you get x1. That is what will be the deflection in the eastward. Now, after that what you do, you take this velocity and again you, in the next calculation, you do v02 is minus gt plus v1c. So it is a kind of do loop that you do, do loop. So you, whatever velocity you get, you again put it back over here. Again you do the calculation, again you put it back like that. It goes, iterations going. And finally you stop somewhere where, it is, it will be very less, or the solutions they match each other. So finally, that way you can get the deflection, you can calculate with v02 corresponding acceleration, second order it is known as. From there you can calculate v2c, and from there you can calculate the deflection in the second order. So this is another way of doing it. Maybe you can write a computer program and you can do that. Interesting. Now, so there are different ways of doing it. So this particular method, if you are interested in, this particular method is given in the book of Dr. Harbola, and this particular method, little bit, not fully, but to some part is given in the book of Patrick Hamill. But we are interested in the approximate solution. Why we are interested in, that is till the first order? Because we want the numbers. As an engineer, we want to see what is the number. Suppose say a body is falling from a height of 50 meters. Then what will be the deflection at the ground in the east direction? That is what we are interested in. Rest anyway, our mathematics, one can do it. But we want to get a feel of it. So let us see the approximate solution. So it is almost the same, only the first order we are doing. So omega is omega sine lambda k cap plus omega cos lambda j cap as usual. V we have taken gt minus k cap. Now, here we would like to take in place of g, ge, but that we will do at the end. At the end, whatever we will get, there we will substitute g as g effective. Otherwise, everywhere we have to write g effective. So first of all, let us do the calculation. At the end, we will write g effective. Second is, here again we are doing the approximation because straight away we are taking gt. But we have seen that it is not gt. In the second order, something else will come. But presently we are going only in the first order and see how much is the deflection. So A Coriolis is minus 2 omega cross V, and if you do the calculation again, so 2 omega gt cos lambda I. So the magnitude is 2 omega gt cos lambda A Coriolis, that is equal to d2x by dt square 2 omega gt cos lambda. From integrating you get dx by dt, this plus c. Okay, just integrate it. At time t is equal to 0, v is equal to 0, c is equal to 0. So finally you get the expression as x, the displacement x is omega g t cube by 3 cos lambda. Now, this is the first order. First order. We are not going into the second order. So, a kind of, this is approximate solution. Now, we are interested in that how much will be the deflection, even it is small or how much. So, this t we can replace by h. How? We know that h is equal to half gt square. Again, it is a very simplistic approximation because h, if there is a deflection, h will not be the vertical h, but something little bit different. But that is very small. So, approximation small here. So, half gt square. This is also, we are taking only g as a acceleration. So half gt square. From there t is equal to 2h by g. Now we replace this t over here, 2h by g, x is equal to this. So you get omega by 3, 8h cube by g. Now here in the last step, we have replaced g with g effective. That means taking the centrifugal term into consideration, centrifugal acceleration. So 8h cube by g effective to the power of half cos lambda. So this is my final term or final answer in terms of h. And this is my final answer in terms of t. Okay. Kleppner has also done the similar way, but he has done it in r theta coordinate. But since we are not familiar with r theta, so I have done it in the xyz coordinate. Secondly, he has solved it for the equator case. And this is not the equator, this is general way of solving at any latitude lambda. Now, we are interested in the number game, that is, if h is equal to 50 meters, that is from 50 meters I am dropping a object, how much will be the deflection in the eastward deflection? So that is coming out to be 0.77 centimeter. 0.7, 1 centimeter is like this, 0.7 is this much deflection. It is quite a small deflection, but okay. So for h is equal to 50 meter, the deflection that you get is 0.77 centimeter at the equator. That is also the equator, that is maximum when lambda is equal to 0. That is towards the east. So well, I hope you have understood the different approaches to the solution, and depending on our need, we can take any one of them. So exact solutions, and this is the approximate solutions, but most important is the physics behind it, mathematics, rigorous mathematics, you can do it later, but the physics behind it should be clear that what actually is happening. Good. So now we will go to the next topic. So this is the vertical motion. Now we will go to the next topic is Foucault pendulum. I hope you know now I suggest you have a glass of water and relax for say 2-3 minutes. Now we will study about a very important and interesting pendulum. This pendulum is known as Foucault pendulum. Foucault was the one who first made this pendulum. So here the pendulum is a heavy mass is there, a massive bob, and it is suspended by a long rope from the top. And obviously at the top where it is hanging, the friction is very less, so that it will keep on oscillating. So what happens that when the bob oscillates like this, okay, so when the bob oscillates, because of the Coriolis force arises because of the rotation of the earth. Because of that, it is again a horizontal movement. This is particularly a horizontal movement we are studying now. The other one was a vertical movement. So here the bob will experience a Coriolis force, and because of that the plane of rotation will keep on changing throughout the day, and it has a period, maybe within a day or more, it will complete one full rotation. That means it is rotate like this, it will keep on changing its plane, and in one full day, I have seen a Foucault pendulum in the Jaipur only. There is a center, Vigyan Bhavan, Science Center, and in that it was there. But few years back I asked about it, but somebody told that it is not working. But it was there, and the people keep it, the sands are kept inside that bob, and you can see the full trajectory, the nice trajectory that it is making throughout the day. Very nice and interesting pendulum, and if it is working, we can go someday and visit that. So this is a Foucault pendulum, a rough diagram which I have made. So basically the bob swings and the plane of motion, it precesses. It is precessing. So it is doing like this, precessing actually. So it is completing the whole circle. That is what, you can write omega also here, or theta dot you can write over here. Okay. So how to go about it? How to solve this problem? Now, in a pendulum, we know the two real forces are there. That is the force of tension and the force of gravity. So they are real forces. Other force is the fictitious force. That is your Coriolis force. This Coriolis force, this gives rise to precession. Now let us understand the problem. First of all, again the coordinate system and the axis. So let us see how is our omega and how is our v, because Coriolis force means omega cross v. So we have to choose a coordinate system. So this is again the same diagram, Earth, which is actually rotating, and the omega you can do omega over here. Okay. Now Earth is rotating, and suppose say the object is somewhere here. So this is my g-axis, z-axis, and this is vertically my omega. So what I do over here, that our purpose is to study the horizontal motion. So if I resolve the omega horizontal component and the vertical component, the horizontal component will not give me anything because it is on the same plane. So cross product will give rise to the 0, same parallel components. The vertical component will give me the product, the finite product. So let us resolve omega into horizontal component omega h and the vertical component omega v. So omega v, as you can see, it is omega sine of lambda. Now let us come to v. In v, what we see that this is the kind of trajectory it is showing. So here it is better with the symmetry problem that we choose here is r cap and theta cap. Okay. So r cap and theta cap, and there it was basically the your z axis. It was along the z axis, so it was k cap. So you may say that what kind of axis is this? This is cylindrical system, cylindrical axis. R cap, theta cap, r cap and theta cap, and the z cap in the direction z. Sorry, k cap. So it is that kind of system we can follow. So this is the motion of the ground, r cap and theta cap. Is this clear? So this is omega and this is of v. Now, so let us see the equations. Omega is omega v k cap. Omega v k cap, vertical component. Horizontal component omega h will not contribute in the cross product. So we are not taking into that. V we can write as r dot r cap. Obviously, r dot is the velocity in the r cap direction. So F Coriolis is minus 2m omega cross v. So minus 2m omega is omega v k cap cross r dot r cap. That gives rise to minus 2m omega v r dot k cap cross r cap. So k cap cross r cap is theta cap. Okay. So now my component is my answer is minus 2m omega v r dot theta cap. So once we get the force, now let us write the force equation. That means the equations of motion. We very well know how to write the equation of motion in polar coordinates. We have studied all this. So minus 2m omega v r dot, that is in the theta cap direction. So we have to use the theta cap expression. M r theta double dot plus 2 r dot theta dot. Now, simplest solution is we take theta dot is constant. So theta dot is taken constant, so r theta double dot is 0. Omega v is omega sine lambda, we have already seen that. Substitute over here, minus 2 omega sine lambda r dot is 2 r dot theta dot. So cancelling r dot from both sides, 2 from both sides, you get theta dot is equal to minus omega sine lambda. Minus means it is in the clockwise direction. So this is the important result we have got. That what is the theta dot? That means what is the angular velocity with which the plane is rotating. That means precession. Now let us try to find out what will be the time period when it will come back to its own position again. So time period for the plane of oscillation to rotate once. Plane of oscillations to rotate once. That will be 2 pi by theta dot. 2 pi by theta dot. Now theta dot is omega sine lambda. Omega sine lambda. And 2 pi by omega is the time period of the rotation of the earth. So 24 hours divided by sine of lambda. So that is the time period. So this is a very, very important expression, that the plane of oscillation, which is actually changing, rotating, precessing, after how long it will become the one again. So that is at 45 degree latitude, at 45 degree, the T is 34 hours for at 45 degree latitude. So find out for Jaipur what will be the time period. That you can find out from this expression. So this is a very interesting expression of the particular problem, that is your Foucault pendulum. Okay. Now the last example. So this is a horizontal motion actually. Again the similar kind of problem. It is the air flow on the surface of the earth undergoes circular motion. On the surface of the earth, if there is an air flow, what will be its motion? How the effect will be? Undergoes circular motion. Let us see. So again omega, and omega you can, so you can resolve omega into, first of all you have to choose a coordinate system, that is your z axis in this outward. Now this axis you can choose as usual your y axis, but presently there is no need for it, so we have not written it. So z axis is this, so we write omega resolving, that is omega v and omega h. Now omega h will not contribute much because it is in the same plane. Okay, parallel components, we will see that. Omega sine lambda, that is omega vertical, is the one which will contribute. F Coriolis is minus 2n omega cross v, minus 2n omega h cross v plus omega v cross v. So we have kept in the vector notation. Well, you can keep it with the unit vectors also, no problem. But here we have kept in the vector notation. Now this term will not contribute because same plane actually. So cross product will not contribute much, but we will see. You see what will happen. Suppose say I take the velocity of the air which is parallel to the surface. It is going from equator to the north pole, which is along the surface. So if you see omega h cross v, if you do it, v is in this direction, v, and omega is also in this direction. Where is the omega? Omega is along the surface. So basically that will be 0. But if it is on the other side, suppose say on the other side, then also omega cross h will give either your some kind of vertical component. Vertical component doesn't mean anything because that is much smaller compared to the gravity. So this component will not contribute anything. Okay, this particular component. Either it will give you 0 or something in the vertical direction that will not contribute to the anything to the gravity, because gravity is much larger. So this is the one which will contribute. Omega v cross d. Omega v is vertical. So vertical cross v, if you do it, omega v k cross v is fh. Now fh will be in the direction of any direction which is actually perpendicular to the velocity. So on the surface of the earth itself. So because of that, you see the perpendicular force, with respect to the velocity, it is a perpendicular force. So it will do a circular motion. The moment the circular motion is there, this force is again on the perpendicularly. So basically it will do a circular motion. But it will do a clockwise motion in the northern hemisphere. Here it will do the anti-clockwise in the southern hemisphere. So this is another problem or another example of how the winds, they are moving on the surface of the earth and how they form the clockwise motion or how they form a circular motion, which gives rise to the weather and weather changes and everything. Not weather change, but it gives rise to a rotation of the wind actually along the surface. So this is also a very interesting problem or example. Now what we will do, we will solve a simple problem, and I would like you to do it beforehand. Like before we solve the problem, you try to do it yourself. So I would like you to have a pen and paper, and also drink a glass of water so that you are fresh and you can try the problem. Okay, so now a problem, a small problem, but I request you to do it yourself first after we read out the problem. A 400-ton train, now you can take any, instead of miles per hour and all this, you can take kilometer per hour also. A 400-ton train runs south at a speed of 60 miles per hour at a latitude of 60 degree north. Find the horizontal force on rails. Okay. So in all these problems, the first step that you have to do, as we have seen, is to set up a coordinate axis. Now different ways you can set up the coordinate axis. Here, the way the problem is solved, the coordinate axis is little bit different from the way we have chosen earlier. So that is why I suggest you that you try different methods and be thorough how to choose coordinate axis. Here we have chosen r, theta, z. R, theta, z. That is your cylindrical system. In the cylindrical system, r is the distance from the axis, not from the origin. Okay, distance from the axis, r. So r, theta, and z. So here r cap, theta cap, and k cap. Let us see. So this is your angle alpha, that is your latitude. We are not drawing now z cap over here. We take the z axis along this. Okay, this is my z axis. So if that is my z axis, so omega is omega k. R is along this direction. As you see, this is the axis of rotation. This is the axis of rotation. So R is away from the axis, R cap, away from the axis. So V is southward, V is southward. So I resolve it, V cos alpha downward along the negative k and V sin alpha R cap. So the components of omega is omega k cap, omega k cap. Here it is V sin alpha R cap plus V cos alpha minus k cap. Now just cross it. So this is 2m minus 2m omega k v cos alpha minus k plus v sin alpha r cap. Just cross. K cross k will give 0. K cross r will give theta cap. Minus sign. So the minus sign is taken inside theta cap minus theta cap. That means minus theta cap means this is your r. Theta is perpendicular to that. That is east direction. So as you see, earlier we had taken x, y, z like that. X was our east direction. Here the same thing we have taken now r. Okay. R is going along this. Now theta obviously will be the direction of east. So minus theta means westward. So you can see different coordinate axes, they give rise to the same result. Only thing is we have to be thorough with it. You can do r theta, you can do xy, whatever it is. So this is a problem which is solved little differently compared to the previous one in a different way. So that we get a flavor of all the different axes. So I request you try to solve it differently also. Okay. Now the assignment. Very simple problem. A plane crossing North Atlantic at 50° latitude was flying at 200 miles per hour. Due east. The navigator went to sleep and the Coriolis force caused the plane to move in circular path. Actually, this problem was given in some midsem or endsem, I don't know. Determine the radius of the circle. Okay, think about it. Very interesting problem. We will discuss in the class. The last one, find the deflection of falling body in south hemisphere. Now that one that we have done, the falling body, we have taken north hemisphere. Now there I did not tell you anything about the southern hemisphere. Things will be little different. Try to visualize first and then you can see some from the book also. So these two assignment problems are there. Try that. Try to find some more good problems. Try to think, try to formulate your own problem. That will be very good. And if you can give it to me, that will be very nice. So this is all about this chapter. But thinking is required more to understand better. So here we see that mostly the centrifugal force, that is anyway is taken care of by G effective. Coriolis force you have to do, and for Coriolis force everywhere you have to find a coordinate system, resolve it, and then do it. Only this problem here we did not resolve much because here the velocity is in general surface velocity. So surface means any direction. So it is better we keep it as omega v and omega h and then we calculate with omega v. Alright. But in most of the problems, you must write the vectors with the unit vectors actually, with the unit vectors, and then do this omega cross v. Good. I think we are through with this chapter and we have finished the 5 lectures. One more lecture I would like to do totally on problems, let me see, and that will be the end of it. Okay, thank you very much, and today is the last day of the year, 31st December. I must thank God for all that we did, and you must equally thank God for all that you got in this year. And tomorrow is the first day of the new year 2023. I wish you all the best. I wish you that you be prosperous, dynamic, and you enjoy at the same time you are productive. Your productivity will bring you enjoyment. So I wish you all the best for the new year 2023. Thank you very much.